our guest speaker, Professor Marius Preda. It's a brief introduction so we can hear more from him. Professor Preda received his engineering degree from University of Politehnica of Bucharest, Romania, and his PhD degree in mathematics and informatics from University of Paris in France. He got an EMBA degree from IMT Business School in Paris again, and he's currently an associate professor with IMT or Institut Mainz Telecom. Professor Preda, sorry if I mispronounce anything, in France. Highlights of his research interests is augmented reality, data compression, video coding, and the list goes on to CAD, computer graphics, computer vision, data structure, and so on. You can read that part yourself. The way that I know him is through his excellent leadership in MPEG, or what used to be MPEG, now it's let's say SC29. And at some point when there was only 2 working groups, he was the chair of 3D graphics subgroup. Now he is the convener of WG7, which is exactly taking on the projects and roles that he was serving when it was a subgroup. So he is the convener of currently the MPEG 3D graphics. As long as I remember, through his leadership, there has been some great initiatives, new projects in that working group, which many of you are familiar. In previous meetings, we got presentations from our experts on point cloud coding. So now here we are hearing it from the convener of that group, and a few of the other, I think, great projects are in the pipeline that Marius Professor Preda will be talking about those shortly. So he has been with SC29 for a long time, and has been an avid contributor to various ISO standards in the fields of 3D graphics, virtual worlds, and augmented reality. With that introduction, I'll give the floor to Professor Preda to present his work or presentation on recent advancements in MPEG 3D graphics compression. Professor Preda, the floor is yours.
Yeah, thank you, Juha. First of all, before starting the presentation, thank you very much for having me here and for the invitation. It's the first time for me to meet your community. It's very nice to see that you are much more than we are in France in SC29, the national representatives. So there are 35 people. Thank you for coming, and it's an honor for me to do this presentation. So what I would like to do here is presentation about what is going on in MPEG 3D graphics coding working group in SC29. But since I assume that several of you are not quite aware about what 3D graphics coding group is doing in MPEG and why it exists, and why we need graphics coding in general, I want to spend some time to go back also on the motivations about what we are doing and why we are doing. So I structured the presentation of today. First of all, I will try to answer to the question, what is this group and why it exists. Then a short chronology about what the group did in the past in its initial form as a subgroup of MPEG, and more recently as a working group of SC29. And then I will spend some time in presenting what we are doing now. So first of all, MPEG 3D graphics coding is an ISO working group within SC29, as you already know, with the aim of developing standards for graphics compression. And I put this compression in red here because ISO already has some other groups, working groups, and SC for graphics in general. We have SC24 that is working on graphics representation, but the compression part is going in SC29, because SC29 is the subcommittee in ISO that is dealing with compression, multimedia compression in general, and also graphics compression. The work we are carrying on in MPEG 3DG is application agnostic. We are trying to cover as many applications as possible, with always the interest of developing compression tools for different kind of applications, which means also different, relatively high variety of data representation models. So while in image domain, the raw data representation is at the end of the day a matrix with some colors for pixels, in 3D graphics is much more complex because we have this huge variety of representation models. And in general, how we do compression is by applying traditional signal processing that are coming from image compression or video compression. And here the keywords like prediction, frequency transformation, quantization, entropy coding are the same that are used also for graphics compression. With a novelty, and I will spend some time to discuss that, same as is done for other medias, there is a relatively important trend today of moving out from this traditional signal processing, or at least partially, to the new methods based on AI. But I will come later on that. So if we want to position in the content pipeline, we have the authoring that can be done by different tools in 3D graphics domain, and here you have some interfaces by the well-known authoring tools for graphics. And on the other side, we have different rendering engines on different platforms and applications, games, stuff like that. And where 3D graphics is doing the job is between them. So as long as you stay in the authoring side, you don't really need compression because the assets are shared locally. And on the other side, if you are rendering 3D graphics, you don't really need compression because the renderer graphic cards need a flat representation. But between them, if one needs to exchange data from production to the user, or from different users or from different production sites, then there is a need of compression. And here is where MPEG 3D graphics is doing the work. Why it exists is like any other media, audio, image, videos, also graphics, and not only 3D, but also 2D graphics needs to be efficiently stored and transmitted. In terms of data size is more and more important, and to be useful in real world application, there is clear need for efficiently transmission and storing. As I mentioned, there are some difficulties, and one which is a key is that graphics representation in general is using a mathematical model, is a parametrization of something, is an approximation of the geometry, or is a color model. So the main question is, shall we compress the model itself, or shall we compress the results when this model was used and instantiated, like an image or like a video? And of course, when we are in compressing the result, then we will already have video and images, and we have technology for that. So the 3D graphics in MPEG, the group is working on compression of different models. And this comes with some difficulties because we have a variety of these models depending on the application, depending on the requirements of these representation models, but also a variety of data type. 3D graphics object is not a unique representation, but is a combination of geometry, material, animation, lighting, parameters, and so on and so on. So little history here, just to understand from where we come. MPEG 1 and 2 was issued in 92, 94, a long time ago. But quite soon after that, in 97, there was a standard core VRML, which was not done by ISO, but later on standardized as well by ISO, that offered representation for 3D graphics in general, in 97. So 1 year later, MPEG took this VRML, which was raw representation, and add on top of it tools for binarization and compression. So back in 98, the 3D graphics subgroup of MPEG was initiated with the objective of applying some well-known technology in compression, quantization, prediction, transforms on top of this 3D graphics compression. And since then, we had a first version of these tools in MPEG for V1 in part 11, that was called BIFs at that time, and in part 2, together with the video coding, actually. Later on, 1 year later, we add new tools for body animation. So in V1, we had face animation, some geometry compression, and already in V2, we had the entire body animation. So illustration that is here comes from a service that was set up in that time, so before 2000, on an augmented broadcasted signal. We had this character here signalizing what the speaker was talking about. So this activity was growing up with the years, and other tools were added for graphics compression in general. For the particular kind of application here, you have a visualization of terrain navigation, and the requirement there was to have progressive transmission, progressive decoding, and then progressive rendering, because you cannot handle the entire terrain at once. So the coding tools had to answer to that requirements. We had some other tools for CAD object modeling, for a more advanced face animation, scalable coding, connection with scene graphs defined by other bodies, and so on. And that work on geometry compression, attribute compression, and animation compression continue to grow up to beginning of 2016, 2017, when we finalized the fourth edition of part 16 in MPEG 4, which is called FX. So you have all the details available on different websites, of course, also on ISO. But what is important to retain is that MPEG 4 part 16 has a relatively rich set of tools, coding tools, compression tools for different shapes representation, textures representation, and animation representation. So maybe there are tools that are covering a relatively important set of applications when you need to transfer assets, to stream assets, to benefit from a good compression factor. Okay, so that was FX. But since let's say 2017, the activity of the group was oriented towards something which is relatively new, and the question that we asked ourselves at that time was, what are the applications where the compression is really needed? Why this kind of question is that before that, creating 3D graphics content is something that is in general incremental. So we are using authoring tools, and we are adding on top of objects different attributes. So it's something that grows up in a kind of constructivist manner. So the compression itself is not something that is very, let's say, important. Of course, people needs to compress, but if you zip, then you may solve your disk problem or transmission problem. So the question was at that time, what are the applications where the compression is really needed? And then a quick answer was, especially because starting with 2017, 2018, even few years before, there were more and more technology available to capture the real world, and not only capture the real world as videos or even immersive videos and then transmit and visualize them, but also capturing the real world and creating something that is more close to a graphics representation. So we had a look on these technologies, and what we found at that time is that, of course, the capturing of the reality is something that is growing up, as you know, from simple images, then adding some stereoscopy, capturing the depth information, which is already information about the geometry. Of course, the technology evolved to have higher resolution, higher color maps, and also up to multi-point capturing. So with different kind of rigs, we can capture around an object or the scene which is surrounding the cameras. And the question when we have this kind of systems is what is the most appropriate representation for? And actually there is no single one, there are several. We can have video plus depth in such a way that at the receiver side, we can synthesize new views based on the video and the depth that was communicated. We may have several videos and the associated depths, but we can also have something else, which is called point cloud, but is a 3D graphics representation, offering the possibility of reconstructing the 3D information before transmission, and then being able to synthesize much easier any view at the receiver side. Point cloud is one, but also mesh is another representation. So there are other groups in MPEG that takes care about the video plus depth, mainly the video group, with different forms. And the more recent standards they are developing is called MIV. And the 3D graphics group in MPEG takes care about point cloud and meshes. Okay, let's have a look what technology is about when we compress this kind of data. We found that the point cloud is the convergence between these two worlds, between the world of visual capturing by using cameras plus sometimes some depth sensors, and the visual synthesis, in the sense that it is a relatively easy to produce representation. It can be of very high quality if the cameras are good quality, but also it gives by design interactivity and immersiveness, in the sense that because it is a 3D graphics representation, we can use a rendering engine to produce whatever viewpoint we need. So we have the immersiveness of the user, but also the user can interact with the content. We are in a pure synthesized world. In few words, what is a point cloud is relatively simple as a representation. Is a set of 3D points. They are not ordered like pixels in the image. So there is no relationship between them. Of course, we can compute distances, but there is no index that we can address directly the point. And each point is defined by a 3D coordinate, x, y, z, plus some attributes that are defined per points. We can have colors in different kind of spaces, but we can also have additional attributes like reflectance, transparency, attributes that are used by the 3D graphics engine when the object is to be rendered. Here are some examples. Probably you already know these examples are coming from sequences that we used for while developing the standard. And this one is obtained. Actually, of course, I present it as a video because we cannot see it in 3D because of our telecommunication system. But what you have to imagine is that when you have a helmet, you can turn around the object and you can see it from different space viewpoints. Some other examples coming from different companies. Here you see a basketball player, and at a certain moment the camera is moving around, and because the object is represented as a 3D object, we can see several viewpoints. And you also notice that the video behind is a 360 video. Another example by Microsoft, when they market the HoloLens, they show this example of a football terrain with people, and everybody here is represented as a 3D object on a field. When we do the mathematics, we realize that for representing one single of this small object, we need something about 1 to 3 gigabits per second per object, which is relatively huge. So it's absolutely clear that we need compression if we want to create meaningful applications. Yeah, some other example. These are applications that are more and more present these days. What you see in this setting, there are two people. One of them is wearing a helmet, an AR helmet. The other one is just dancing. But what this guy can see in the scene, he can see two persons. One is real, and the other one is a person that was captured before and displayed only in the helmet. So it's a kind of AR scenario that is more and more useful today. Not necessarily for dancing, but there are other applications that can be done. And by the way, this person here is represented as a point cloud. Another example, which will have even a bigger impact in our life, is the assisted driving up to autonomous driving. So these systems they are using a LiDAR for capturing the scene, the LiDARs that are on the car, and capturing the scene, and helping the driver with some messages, or even going up to having an autonomous car, because he's able to interpret the obstacles, the signs, and so on and so on. This is not something new, but what is new is that we will have in the future systems that are using multiple cars to capture the world, and there will be a transmission of information between cars, and one of this information to be transmitted will be the acquired point cloud. So this is why the compression is also needed in this kind of use cases. Okay, so a simple slide just to have in mind the numbers. An object like this one is using 800,000 points, and if we want to transmit it in an uncompressed version, is about let's say roughly 1 gigabit per second. Okay, at least. So for sure we need compression. Then the question was, what can we do to compress this kind of data? Let's call it signal, because it's captured from the real world. There are some principles here. One is that a point cloud is a very sparse occupancy of the 3D space, because in general the object is represented by the surface. Of course, we are just capturing how the light is reflected by the surface. We have no information about what is inside the volume. And in terms of prediction and in terms of compression, while in 2D a pixel has 8 neighbors, in 3D it has 26. And many of them are transparent. So you may imagine that building the predictors is a more difficult task. As we may imagine, we cannot, and we will not do it directly in the 3D space, but we need some special data structures, special constructs. And the literature already had an intensive research work in this domain. So this is not new, not invented by MPEG. The OC3 and KD3 are two examples of these structures that are used to represent the 3D space into another space, and which are more compression friendly, let's say. Just illustration explaining what the OC3 is. So we have the point cloud here. An OC3, a 3D OC3, will divide the space in cubes, and the idea is to continue this subdivision into cubes only if a big cube is occupied. So when a big cube is not occupied, just signaling is not occupied, there is no need to subdivide it more. But when it is occupied, we continue the subdivision up to the last leaf. And that will change the XYZ representation into a kind of tree where we, as an example here, we encode 1. It means that this cube should be subdivided more. And of course, this is a 2D example. It will be subdivided in 4. And then if there is a need to subdivide, so on and so on. So we may imagine that this hierarchical graph has much more redundancy, that it can be exploited by coding tools than the initial 3D representation. Another one is KD3, but I will not go in detail, is just another way of segmenting the space. So still, there are some issues here in the sense that these kind of structures are good for static scenes, but we are in MPEG, and one of our objectives is to compress moving pictures, so moving scenes. The problem is that when we do this kind of partitioning for, let's say, one frame of the object, what it may happen is that we have this small cube which is occupied here, and at the next frame, it is possible that this point here jumps somewhere there. But the big cube before was empty. So it means that points from here can jump in the hierarchy very high. And that is not very good for prediction, because we have, let's say, like we have in video, we have to force an intraframe. Okay, so while there are things that can do a good job for static objects, for dynamic, we have to do something else. Okay, so this is what we did. We understood the need of point cloud compression back in 2014, and as all the MPEG projects and in general standardization projects, we start with call for evidence, and then we prepare the data for call for proposal that we had in April 2017. And actually, in April 2017, we had the call for proposal and then the answers in October. And we had 9 leading companies around the world, of course, who answered to that. And we end up in 2020 by FDIS of two standards. One is VPCC and the other one is GPCC. And both are for point cloud. And now the question is why we did 2 standards and not only one. We actually, from the beginning, we observed that the point clouds are different depending on the application. you may have dense point cloud, you may have sparse dense cloud, of course, you may have static or dynamic. So it was quite obvious from the beginning that the same coding tool cannot fit all the requirements. So the first one was the video-based point cloud compression, and the main ideas to create this standard were inspired from graphics. One of this idea is what we call in graphics displacement mapping. So sometimes instead of defining geometry like a set of triangles and attributes, we are generating the geometry based on an elevation map. So by using this image, we can create at the rendering phase a geometry. This is called displacement map, and this is one of the idea we used in VPCC, and I will explain how. The other idea, also inspired from graphics, is the texture mapping, and the way how the objects are colored in 3D graphics is that we have with the geometry an associated texture map where portions of the geometry are projected in this image space, and the color that is in the corresponding pixel will be used to color the 3D point of the object. And everything else between the two pixels here in the image or two vertices here in the 3D model will be used by copying the value of the corresponding pixel. This is also something well known in 3D graphics. So based on these two ideas, the way how we decide to code the point cloud was to have projection planes. So you may imagine this is our object, and then we will project all the points from the object on a plane, and we will encode the distance with respect to the plane, which will give a kind of depth, and the color of that point will be encoded as the color of the pixel in the plane. Okay. Of course, it's not as simple as I'm explaining, in the sense that it may be possible, because we have a 3D object here, to have several points that will be projected in exactly the same plane pixel. And then we have to store different colors and different depths. And to avoid this situation, actually, what we are doing is, instead of projecting the entire object, we are cutting the object in what is called patch, and each patch is projected on one of the planes of a cube. To give even more adaptability, we add 4 additional diagonal planes. So the projection space looks something like this. We have the cube's faces plus the additional faces, and each patch will be projected to the plane that gives the less projection distortions. Okay. And once it is projected, what we keep is the distance with respect to the plane and the color in the pixel domain. So what this transformation gives, so here we have the 3D space that was segmented into patches, projected on different kind of planes, and what we obtain is a geometry image giving the distance of the point with respect to the plane, plus the color that is associated to that point. So in one sense, a 3D representation was transformed in a 2D representation by, let's say, an intelligent projection. Of course, not all the pixels, because we are transmitting these images, videos, and we decode them, and we observe that some pixels are not useful for the reconstruction. So we have to signal that to the decoder. So this is why we have an additional occupancy map indicating which of the pixels from these maps are to be reconstructed. That gives a good approximation, but still some points are still projected in exactly at the same position in 2D, and this is why we can add as many maps as required. Okay, and that gives a very good approximation. And if at the end of the day we still have points that are not well projected, they will be encoded separately in such a way that we have bijectivity between this 3D space and these collections of 2D maps. Just illustrating that for the walking sequence that you saw before, this 3D object walking is represented now as a set of images. And since MPEG is very good in video coding, we may say the problem is solved. We can use classic video codec to encode this 3D representation. Of course, it's not as straightforward as I'm saying it, because even if you look at these images, you notice that these are not images for which the video codecs were designed. In the video, we have other type of information in the sense that it's more fluid. We can nicely obtain the motion vectors. So this kind of content, let's say, is not video codec friendly, but still is possible to code with video. And the question is now what the group is doing next. In terms of the form of what we call is next is a kind of, we are talking about explorations, about preparation of the proposals and so on. So one of the topics which is in exploration is the AI based compression. This is something that becomes to be very important in general for the technology development, for media compression, because it's not only for 3D graphics, but we have more and more papers and work on showing that AI based methods can provide good compression performances for images, and more now publications related to video coding, and few of them about graphics coding based on AI. So we started an exploration. This is something like 1 year before, 1 year and a half maybe, trying to see what are the possible performances of these approaches for 3D graphics. And what we are doing in terms of technical work, we are investigating the different AI frameworks that can be applied to 3D graphics compression, and in particular to point cloud compression. We are investigating different models, neural network architectures. Of course, a lot of and important work is on data sets, because these AI approaches are using content for training. So data set is a key factor. What should be used for training them to learn the models. We have some works on comparisons between different existing models. What are their performances in terms of compression, but also in terms of complexity. As a group, we are interested in having AI compression approaches for the entire object, including geometry and attributes. In general, the scientific literature at least is focused on geometry only. Very few of them are addressing attributes. And by the way, there is much more bitrate that is usually spent on attributes than on geometry. But people like geometry. That was also the case with the traditional methods. We had a lot of publications on geometry and much less on attributes, despite the fact that the real impact is on the attributes. Also, we are interested in static and dynamic point clouds. Work is published on dynamic but the group is in that direction. In general, comparing this work with the traditional way of developing standards for compression, we realize that is something that is much more complex. With the AI approach, this is something much more difficult to set, because we know that the performances of a model will depend even about the data that is used for learning. So the activity is continuing, of course, with the objective to, at a certain moment, to have a call for proposal and look for technologies to define a new standard, one or several, we will see, that are using this new trend in technology development, which are the AI-based methods. We are producing at every, let me just check that I'm still online. I am. We are producing at every meeting 3 important documents that are improved at each meeting. For newcomers interested in this activity, that would be the starting point. So a document is about guidelines on how to conduct AI exploration experiments. A second is related to the data set, and the third one is related to the way how the performances are analyzed. A second new topic is the mesh coding, with the specificity that here we are not talking about traditional mesh that was defined with a geometry that is changing the vertex positions plus the attributes, but we are here referring to a mesh that is changing both the geometry and the connectivity in time. So this is defined temporarily as a set of points that are moving in time, but also as a set of triangles, let's say, but polygons in general that are moving in time. 2 years to prepare for proposal. Of course, all the exploration that was done before. We issued it in last year, in October 2021. We received the 5 technologies, full technology, and after performing whatever was needed in terms of evaluation, performance evaluation, so subjective and objective, we were able to declare a winner. That is the base of the new standard. So in conclusion, there are 2 flavors for point of compression. One based on video that will allow a rapid deployment because the entire video ecosystem is reused, encoding units, transmission, decoding, and on top of that, only a very light layer that is usually in software to reconstruct the 3D object. And for the objects that dense, like for the assisted driving, autonomous driving, we have this solution that is called GPCC that has, in theory, the potential to do better compression, but of course, the activity on video coding is so advanced that it will need some time for GPCC to be able to compete in terms of bit rates with VPCC. Okay, so as a conclusion, PCC provides this solid framework of the convergence between the natural and synthetic 3D graphics. We have on one side different and more solutions to capture the real world and have a representation that is able to reproduce the receiver side pixel domain, pixel plus depth, at MPEG, but also in the synthetic domain because of the reconstruction of the 3D objects and the 3D. So I think that I will stop here. And if we still have some time for questions, I'm very happy to try to answer.
Thank you so much, Professor Preda.